So we had started off with rate of reaction, right? We had sort of equilibrium ne khatam kar liya tha. We not completely, not entirely, but rate of reaction is something that is linked with it. So I told you that if you want to figure out the speed of the reaction, so what you have to do is you have to figure out a change, how fast something is changing. Lots of changes can happen in a reaction. Okay, all reactions are kind of different. Okay, some have bubbles forming, some are there's color change happening, there's mass, something happening to the mass. So if the change happens very quickly, the time is less, the reaction is faster. If the time taken is more, the reaction is slow. So we started studying this particular reaction, and I told you that what you're going to do is, so now about this, I told you that you're going to try and figure out a change and how fast that change happens. So one was that how quickly does Mg dissolve in the acid? This is Mg in an acid, and we're going to figure out how quickly it dissolves. Like I can plot the mass of Mg with respect to time. Initially, reactions are usually fast at the beginning, and then they start slowing down. So initially, Mg dissolves at a very fast rate, its mass decreases. I mean, this axis is time. So initially, Mg dissolves, and then it slows down. So I told you about the slope of the graph. Whenever you plot a change with respect to time, the steepness or the slope of the graph gives you an idea about how fast the reaction is. So the graph is steeper, that means it's faster. If the graph is less steep, that means it's a slow reaction. So same thing. Another thing that we can do about Mg plus HCl was that I can plot the volume of H2 gas that's forming. So again, it's a change that's happening, volume of H2 gas that's forming. Initially, there would be no H2 gas. And over time, there's going to be more and more H2 gas formed. So the amount of H2 gas would go up. It would increase with time. And the gradient would be very steep initially. But then what's going to happen is that the gradient would become less steep because the reactions usually slow down over time. So the gradient becomes less steep. So it's fast in the beginning, slower at the end. So steeper indicates faster. It indicates faster reaction. So what other change could be plotted with respect to time? I mean, we can do lots of other things when we study a rate of reaction, but it is basically at the end of the day, it's any change with respect to time. Any change, kahan pe gaya hamara formula? This one. So it's basically at the end of the day, it's any change with respect to time that's plotted for a reaction. That would give you an idea about how fast the reaction is. Is this clear, this thing?
Yes.
So what we're going to do next is that the reactions that we are studying, they can speed up, they can slow down. And we're going to discuss why reactions speed up or slow down, the factors that affect the speed of a particular reaction. So let's say I'm starting with the first one. So we're now going to study factors that affect the rate of a reaction. So many factors, starting with the first one. The very first one is temperature. Reactions happen at a faster pace if you've got a higher temperature. Now, one thing that you have to understand about reactions is that all reactions, they happen because of collisions. And there are two types of collisions. When we talk about collisions, let's say there's some molecules, let's call them X. Okay, so you've got these molecules. And there are these other types of molecules. Okay, let's give them a blue color. So I've got these two types of particles. And these two types of particles are going to bump into each other. They're particles X and they're particles Y. Okay, let's go. I mean, there could be any atom or molecule, and they're going to bump into each other. And when they collide, a reaction would happen. So reactions, they happen due to collisions. Okay, so these two particles are going to react. Now, there are two factors. When we talk about collisions, you have to think of collisions in two ways. Number one, the first way is how frequently do they collide? So there's a frequency of collisions. Like how much do they collide per second? Like if they're colliding a lot, then there's a very bright chance of the reaction happening at a faster rate. Okay, like in 1 second, the two particles are going to bump into each other like a million times. Then that means the reaction would happen really, really, really quickly. If the two particles are really slow, and let's say they just have 10 collisions every second, then the chances of the reaction happening at a very fast rate is lower. Okay. So pehla point, is this point clear? Yes or no? Is this clear? Vasa, is this clear? Zainab, Saneem, is this clear?
Yes, sir.
Ji, sir.
So the second point is the effectiveness of the collisions. Or we can say how successful are the collisions? So this particular point, what this point means is that if this red particle were to collide with the blue particle and there was going to be a reaction. So how strongly do they collide? What is the force with which they're colliding? Do they have enough energy? Because when particles collide, they need to bump into each other with a lot of force. That leads to more successful collisions. So there's a successfulness of the collision. Like if particles bump into each other 100 times, not every time is there going to be a reaction. You've got particles bumping into each other, but if they're bumping or colliding with not enough force, then there's very little chance that a reaction happens. They need to really, really strongly and vigorously bump into each other. So effectiveness of collisions is that if particles have low energy, or insufficient energy, so if particles have insufficient energy, then there's a lower chance of a successful so the particles really have to vigorously collide with each other. It's not just only the collisions that are happening, but the collisions have to be successful. Okay, if particles collide 100 times and not a single time is there a successful collision, then the rate of the reaction would be exactly 0. Nothing is happening. Although they are colliding, but it's not leading to a reaction. Okay, it's like somebody trying to break a piece of wood. If you don't hit the wood with enough force, there's not going to be a reaction. It's not going to break down. Okay, so this is what you're doing to atoms. When atoms and molecules they collide, they kind of break down and new things are formed. So the collisions have to be effective, they have to be successful. So we're going to discuss collisions in two ways. One is how often are they colliding, and do the collisions lead to a reaction or not? Are the collisions successful? Like if they collide 100 times, how many times does it lead to a reaction? So we're going to think of it in two ways. So the first factor is temperature, and the rule is that whenever you increase temperature, you always pretty much get a faster reaction. And they're going to ask you, why do you get a faster reaction? And the explanation for that is that particles have more kinetic energy. So they travel faster. And that means they're going to bump into each other a lot more. So you get more frequent collisions. And you also get more effective collisions because they're traveling faster. So you're going to have more effective collisions as well. They bump into each other with a lot more force. So they bump into each other with a lot more force. So is this point clear that whenever you talk about temperature, you're going to think of it that increasing the temperature increases the kinetic energy. So you get more frequent collisions. Plus, at the same time, you also get more effective collisions as well. Okay, so that is the effect of temperature, which is why the reaction usually speeds up. Okay, is this clear, everyone? Hamza, is this clear?
Yes, sir.
Okay. So let's move to point number 2. And you have to remember, use the two terms. Okay, you're going to talk about the frequency of collisions, and you're going to talk about how successful they are, the effectiveness of the collisions. Now, point number 2 is pressure. Now, when it comes to pressure, remember this pressure only affects gases. That's it. Only your gas particles are going to be affected. Why? Because only gases are compressible. Solids and liquids are not compressible. So pressure is not going to have any effect whatsoever, as they are incompressible. So pressure is not going to have a as they are compressible. Sorry, I was talking about solids and liquids. So solids and liquids are not compressible. I mean, this is what's going to happen. Like if I take a piston and on top of the piston, there is, let me just, and we've got, so we've got this movable piston. So I've got this movable piston, and I've got my particles. There are two particles of X, and there are three particles of, let's say, Y, three each. So at the moment they're far away. Okay, this is a low pressure situation. In low pressure, you've got a larger volume. Okay, I'm going to start compressing it. Low pressure, gas particles are far away. So at the moment, the gas particles are far away. So they would have to travel a longer distance to meet each other and to collide with each other. So at the moment, the reaction would be slower because they're further away. So you're going to get more frequent less frequent collisions. They won't hit each other that frequently. So you're going to get less frequent collisions. But then let's talk about the high pressure situation. So what I'm going to do is I'm going to start increasing the pressure. Just 1 second. So what I'm going to do is, let me move this. As a same gas, the two particles want to bump into each other. They're going to react with each other. But what I'm going to do is I'm going to start increasing the pressure. To increase the pressure, I'm going to start applying force from the top. And all these particles, they're going to become a lot closer together. I'm going to squeeze them. I'm going to compress them. So from the top, I'm going to start applying a force now. I'm increasing the pressure. And the piston now starts to move downwards. So this piston starts to move downwards. And it has now compressed the gas. Now you can see that the particles are a lot closer together. They've been squeezed together. So they're going to bump into each other a lot more. You're going to get a lot more frequent collisions now. Okay, so now at higher pressure, so they are compressed, lesser volume. So gas particles are a lot closer. And you get more frequent collisions. So that means you're going to get a faster reaction. But remember, compression can only happen in gases, not in solids, not in liquids. I mean, this phenomena, it only happens in gases. So high pressure, you're going to have a lot faster reaction because the particles would be closer together and they're going to bump into each other a lot more. Okay, is this point clear as well? Yes or no? Is this clear?
Yes, sir.
अच्छा, अब ये के the next one. So that's pressure. The next one is, 1 second. Factor number 3, that's concentration. And when we talk about concentrations, we're talking about solutions. What concentration stands for is the number of particles per unit volume. Like if I have a solution, so this is one container, this is one beaker, and here's your other beaker. They both have some solution in them. one is more concentrated than the other one. So let's say this is the first one, and there are 3 particles of substance X and 3 particles of substance Y. So X and Y are going to react with each other. They're going to bump into each other, and that would lead to a reaction. Here's another container, and this container is a lot more concentrated. That means that the amount of particles per unit volume is a lot more. Now, because of this, that would lead to a lot more frequent collisions. So you've got higher concentration. So that means you've got more particles per unit volume. And they would be closer together. Which is why you're going to get a lot more frequent collisions. Is that clear? Yes or no? Is this clear?
Yes.
Hamza, is this clear?
Yes, sir.
I said that would lead to a faster reaction. Now, number 4, let's talk about number 4. The 4th factor is surface area. Now, this 4th factor usually applies to solids. So whenever you try to react a solid, you can do 2 things. You can either take a solid lump, take a large piece, or what you can do is you can have a lot more smaller pieces. TK, you can have really, really tiny. I mean, you can break it down and crush it. TK, you can have smaller pieces. Or you can just make it powdered. So there are 2 ways you can, if you're trying to react a solid, you can either take a large lump or you can take smaller pieces. Remember, smaller pieces have greater surface area. There's going to be more frequent collisions. Which would lead to a faster reaction. So here's what that means. Like if there's some red particles that want to react with the solid, and all these red particles are coming in and they're trying to bump with the solid. Now the surface area is really less. Only the particles that are at the top surface are able to react. Only these ones, the ones that are right at the surface, they're the ones that are exposed, and they're the ones that are going to react only. All the ones that are inside, they will not be able to react. They will not be able to take part in the reaction. So that effectively means that there's going to be far fewer collisions because the middle ones are not able to react. The top surface is able to react, but not the middle one. Is this point clear? Amna, is this?
Sir.
But when the same substance is in powdered form and you've crushed it into really tiny pieces, and the red particles, they come in and they try to react. Now, all the red particles can kind of react with almost all of the blue particles. They can bump into them and they can react with them. So over here, the surface area is a lot more because every particle is exposed. Every particle surface is exposed. Every particle can take part in the reaction. It can bump with the red particles and react. Over here, the middle ones cannot react. Only the ones that are present at the surface are able to react. So remember this, whenever you use smaller pieces, they always have greater surface area, and that would lead to more, that would lead to a lot more frequent collisions. So yes, so is this also clear? Laiba, Hamza, is this clear? Saad, Zainab, Sareem?
Yeah.
And then we move to the last point. And so remember, we've discussed 4 factors that affect the rate of the reaction. So one thing that that you will see is that I'm writing some of the fact. For example, this one. I talked about the frequency of collision, and I at the same time talked about the effectiveness of collisions. But I'm usually using one of the terms. In temperature, I had used both. Because when you increase temperature, not only do they, because they travel faster, not only do they bump into each other a lot more, that means that leads to frequent collisions, but you also have more effective collisions as well. I mean, they travel faster, so they collide with each other, bump into each other with a lot more force. So that means the successfulness of the collision is a lot more. With pressure, I only use the term, I only use one of the term, and that was the frequency. More, you just get more frequent collisions. I didn't use effectiveness of the collisions because when you increase pressure, the only thing that's happening is they just bump into each other a lot more. The force with which they're bumping into each other is the same. The only thing is that they're just you're just having a lot more frequent collisions because the particles are closer together. The same was true for concentration. Like I'm not giving the particles energy, so they're bumping into each other with the same force, except they're closer together. So they at a higher concentration, they're closer together, which is why they're going to be more frequent collisions only. That's it. And the same is true for surface area. In surface area, the particles are simply just bumping into each other a lot more. You just have more frequent collisions. The effectiveness of collisions is kind of the same. The successful rate of the success rate of the collision is almost the same. It's just that they are going to collide with each other a lot more frequently. And the last one is when I reach catalyst. Okay, point number 5. Now, if I add a catalyst, what happens with a catalyst is that it lowers the activation energy. And leads to more effective collisions. The frequency or the number of times they collide with each other, that kind of remains the same. So let me elaborate both these points. So here's what happens when a reaction happens in a bit more detail. For example, I've got H2 reacting with Cl2, and they're going to form 2 HCl molecules. So here is what happens when a reaction happens, and let me open a new page. So I've got an H2 molecule. The H2 molecule is, I mean, the two are bonded together. I've got another H2 molecule. I've got a Cl2 molecule. And I've got another Cl2 molecule. The two molecules are going to bump into each other. They're going to come and they're going to collide. So this molecule over here would be traveling, and it would travel and it would hit this other molecule of Cl2. So this Cl2 molecule and the two are going to collide. Now, when they collide, the very first thing that always happens is when a reaction happens, old bonds are broken. I mean, that's why they need to collide. I mean, that's like if you're every time when two things collide, something breaks. And this is what happens when molecules they collide, when atoms collide, the old things they must break. The old bonds they need to break. So during collisions, let's say they collide, the Cl2 and the hydrogen atoms, they all kind of break. Right? And the atoms kind of break and the old bonds are broken. Okay, is this point clear? What happens during a collision? Yes or no? Is this clear?
Yes, sir, it's clear.
So the old bonds need to be broken. That's the first thing. And then the next step happens. Then there's going to be a lot more collisions. New bonds are formed now. So now imagine the H atoms and the Cl atoms now freely moving around. See, so you've got this H atom, which is just roaming around. You've got a Cl atom, and that Cl atom is roaming around somewhere, and then they bump into each other. Right? I mean, they're in a container, they're just flying around. They got broken in the first collision. Now they collide with each other, and now that leads to the formation of HCl. The two bump into each other and they form a new bond, which is HCl. So in every reaction, two things usually happen. Not exactly in this order, but this is what usually happens. The old bonds need to be broken, and then the new bonds are formed. And something new is formed. The atoms kind of rearrange themselves. During the first collision, the hydrogen bonds between the H atoms that broke and the Cl-Cl bonds that broke. The atoms got freed and they were flying around, and they're flying around and they bumped into each other a second time. And now an HCl molecule is formed. And that's how your products are formed. So the problem is the first step. Whenever a reaction happens, some energy is needed to break the old bonds. A lot of time, the old bonds are very strong. So some energy is needed to break the old bonds. Particles need to bump into each other with enough force. To bump or collide with enough force. To break the old bonds. So what I need to do is the particles need to sort of bump, and they need sufficient energy that they violently collide and all the old bonds broke. Okay, so some minimum energy is required. It's not that they just roam around with very less energy, they travel very slowly, and they just have this tiny collision and you expect something to happen. It's not going to happen. Some minimum energy is needed. That this particle would be traveling with sufficient kinetic energy, this other particle would be traveling with sufficient kinetic energy, that when they bump into each other in the middle, the old bonds broke. So some minimum energy is required for the reaction to happen. Is this clear? Yes or no? Bakio clear? It says Saad, Zainab, Sadeem, is this clear? Hamza?
Yes, sir.
Yes, sir.
So that's known as your activation energy. And this is what we are talking about here. Activation energy EA is the minimum energy needed to start a reaction. I mean, like, if you strike a match and you try to light it up, you have to strike the two things with kind of sufficient force. There's a minimum force that you have to use so that the particles bump into each other and the old bonds break and then new bonds are formed, which is why fire or heat is produced in that reaction. So activation energy is the minimum energy that is needed to start a reaction. So I'll just take 2-3 more minutes to explain. There's some minimum energy that is needed to start a reaction. Basically, why do you need energy? To break the old bonds. So what does the catalyst do? A catalyst, what it does is, because your whole reaction is slowing down because of this. Sometimes what would happen is, like, you've got N2, which has a triple bond, and you've got oxygen, which has a double bond. Now these bonds are very strong. So if these molecules, they bump into each other, maybe their old bonds will not break. So this reaction has very high activation energy because the bonds are really strong. So like if you can't get rid of the old bonds first, you can't free up the nitrogen atoms and the oxygen atoms, you can't expect something new to be formed in the first place. So it's got high activation energy. Let me put insert H2 over here. So what a catalyst does is, catalyst kind of makes it easy to break the old bonds. I mean, this is the bond that's stopping the reaction from happening. Like, it's very hard to actually break this bond. So catalyst makes it easy to break your old bonds. So in a way, it lowers the activation energy. So catalyst is a thing that is added to a reaction. The whole problem was that breaking the triple bond was very hard. So you had to give it a lot of energy, and you had to pump the two molecules. You had to collide the two molecules with a lot of force. But adding a catalyst makes this part easy. So it lowers the activation energy, and when the activation energy is lowered, you get more successful reactions. It lowers the activation energy, and you get more effective. I mean, this is what's happening. The frequency of collisions is the same, except that you now have a lot more effective. You've got a lot more effective collisions. I mean, you still have 100 collisions, but previously only one was successful. Let's say out of 100, only one was successful. Like in this reaction, the molecules were bumping into each other. Out of 100 collisions, only one was successful. By adding a catalyst, it made it easy to break the triple bond. Now, out of the 100 collisions that happen, let's say 50 of them are successful. So you get a lot more reaction now. Is this point clear?
Jason.
Okay, so is the role of the catalyst clear? Yes or no? Hamza, is this clear? Saad, Zainab, all clear?
Yes, sir, it's clear.
Sure. So remember these 5 factors, and remember, I'll just quickly repeat that. The first one, temperature, it increases both effectiveness of collisions and the frequency of the collisions as well. Pressure, surface area, concentration, they only increase the frequency of collisions. Catalyst increases the effectiveness of the collisions. So these are the 5 factors. You add these 5 factors, the rate of reaction speeds up. So let's talk on this a lot more. Then we'll continue tomorrow. Okay, everyone.
Allah Hafiz, sir.
Take care. Allah Hafiz.
Love, sir.